Hello everyone, our experiment today is about wavelength. The aim of our experiment is to determine the wavelength of visible light. Now let us learn about how the light waves get diffracted at an aperture. According to the definition, the bending of wave is deviation from the original direction of propagation when it meets a small obstacle is called diffraction. Hence, for the experimental observation of waves like diffraction needs small size obstacle. Thus, diffraction is defined as the bending of light waves around an obstacle whose dimension is comparable to the wavelength of the incident light. As you can see in the picture, if we imagine a plane wavefront incident on a narrow slit, all the waves shall arrive at the slit in the same phase. Let the wave proceed toward O, the center of the screen directly perpendicular of the lens, or the end of the dotted line in the screen as you can see. Therefore, a shape image of the high intensity will be produced at that point. But according to the wave theory, every point along the slit will be the center of the secondary wavelets. Let us consider a point P on the screen such that wavelets reaching P make an angle theta with the direction of the incident plane wave. The wavelets start from the different parts of the slit in the same phase, but they shall not arrive at P in the same phase because they will cover an equal distance in reaching P. So the only effect will due to this path difference lambda between the extreme rays. And so every strip or slit in the upper half together with its corresponding strip in the lower half will cancel each other effect. Ultimately, it follows that P will be the dark point. If the width of the slit is d, then we have n times lambda equals to d multiplied by sin theta, which is n expressed the order for each slit. And the right side of the picture tells us about the schematic illustration of tool setup of this experiment. Material and tools. The first thing is the natrium lamp, and then the diffraction grating, angle scale, and spectrometer. Procedure. The first thing you have to do is to keep the collimator and the telescope level in the same level and straight. Also adjust the width of the slit so that the image that appears from the back end of the telescope is a yellow vertical straight line. And place the diffraction grating on the optical bench in the center of the spectrometer with its clamp in a perpendicular position to the direction of the beam coming from the collimator. As you can see there, you can write down the angle position both for the left side and the right side later. And as you can see in the screen, the yellow line that appear will correspond with the angle position you set up. And if the foot of the telescope is shifted or moved to the right slowly, the yellow line will disappear from the view and it will reappear with a weaker intensity. This is the diffraction position of the order n equal to 1. And also don't forget to read the position of the diffraction angle after the yellow line coincide with the cross thread. As you can see, in the left side, the upper on the screen is the screen that captures the yellow straight line. And also the left side in the bottom is the position of the angle. Here is your data. Based on the table as you can see in this video, you will get the information about the right position and the left position of the diffraction angle. that you already did in the previous procedure. And also from this data you have to calculate the wavelength of the light. So be careful on your calculation, discuss with your teaching assistant, and do your report. Okay, then I want to remind you again about about your task. You have to determine the wavelength of a natrium lamp. As you can see in our procedure, we use a natrium lamp in the spectrometer. Then you have to calculate the wavelength of this natrium lamp. Thank you, good luck for your report, and see you in the next experiment.